In this lecture, let's revisit the relationship between partial derivatives and our derivative as a linear transformation. As I indicated when I last spoke about this, the existence of partial derivatives does not imply that the function is differentiable. But as we'll see, a mild extra condition on partial derivatives will ensure that. So let's write down the theme for today's lecture: partial derivatives and differentiability. So let's make the following definition. As usual, U is an open set in Rn. F from U to Rm is some function. We say that F is continuously differentiable if F is differentiable and we would like to say that the derivative is continuous. So, and that's what we can do is, to make that precise, we can look at the derivative as a function from the open set. At each point of the open set, I have the derivative, which is a linear transformation. So I have a map from U to L, Rn, Rm. So this map or function from the open set to the space of linear transformation, this should be a continuous map. Now, to talk about continuity, of course, we need metric spaces. U is anyway an open subset of Rn. As for the right hand side, the range, this is a vector space and it has lots of norms. So the norm we'll be dealing with is the operator norm. So you can say continuous with respect to the operator norm. But as we discussed a couple of lectures ago, it doesn't really matter which norm you use. The right hand side is a finite dimensional vector space. But for practical reasons, we'll work with the operator norm. So now that's the, so where do partial derivatives enter into the picture? So here's the theorem. By the way, I forgot to introduce the notation here. We write F in C1 as shorthand notation for saying that F is continuously differentiable. So F in C1, if and only if djfi exist for all j equal to 1 to n, I equal to 1 to m. All the partial derivatives of all components exist and are continuous. So we already know that if a function is differentiable, all partial derivatives exist. Here we are going well, here we are saying a couple of extra things. One is that if the function is continuously differentiable, not only do the partial derivatives exist, but they themselves are continuous as well. And the more relevant thing is the converse direction. Namely, if partial derivatives exist and are continuous, then the function is differentiable. And in fact, the derivative is also continuous. So let's prove this. So first let's do the easier part. One is, suppose f is in C1. Then we would like to say that the partial derivatives are continuous, exist and are continuous. Well, we know how to, when we talked about partial derivatives for the first time, we saw how to recover partial derivatives in terms of the derivative as a linear transformation. In fact, what we had was we had proved this equation f prime x acting on Ej is I equals 1 to m, the partial derivative of fi x acting on ui. So we had proved this earlier. So if I want to isolate one part, so this is a sum of partial derivatives. Well, now this here this notation ui is u1, u2, um is the standard basis of Rm. E1, E2, En is the standard is the notation for the standard basis of Rn. So these partial derivatives are occurring as coefficients on the right hand side, but if I want to isolate one of them, all I do is I just take the inner product with let's say if I want the dj fi naught, I take the inner product of the right hand side with ui naught. So this implies f prime Ej inner product with ui is dj fi at x. This immediately proves that so let me write that again. So dj fi x is f prime x Ej inner product with ui. Well, this will immediately prove that this is continuous. The dj fi, these are partial derivatives are continuous because we can directly check in fact. So dj fi x minus dj fi y absolute value is equal to f prime x minus f prime y. This is a linear transformation acting on Ej in a product with ui, absolute value of the whole thing. Then I use Cauchy-Schwarz to get this is less than or equal to norm of f prime x minus f prime y ej, then norm of ui, which is 1. So norm of is 1. Now, using the definition of the operator norm, this is less than or equal to, this norm here is just the Euclidean norm. So if I now bring in the operator norm, this will be less than or equal to f prime x minus f prime y norm, and then multiplied by norm of ej, which is again 1. Norm of ej is 1 as well. So we are done. So this last thing here is the operator norm of f prime x minus f prime y, and we know that by assumption we had that this thing here, f is in C1, so f prime is a continuous map. So therefore f prime x minus f prime y can be made arbitrarily small, and depending on, given epsilon, I can make this less than epsilon for suitable x and y. Therefore the same holds true for the partial derivatives. For the other way around, so now suppose that dj fi from u to r is continuous for all I and j, suitable values of I and j. Well, so we would like to see how we can get the continuity of, let's see how we can get the continuity of the derivative as a linear transformation. Actually, since we have to first show that f is even differentiable in the strong sense. So let's do that first. So let's write down f of x plus h minus f of x. The idea is simple. It's just that I would like to, so basically I want to use the same formula. See, remember that I had this formula f prime x acting on ej in terms of partial derivatives. This of course tells me that since I know f, so I know if the derivative exists, its action on ej is given by this. So now I know the right hand side exists, and if I can show that somehow the partial derivatives serve the same role as what f prime would do if it existed, then I would know by uniqueness of the derivative an appropriate combination of partial derivatives should do the job. So the idea is to somehow write this in terms of partial derivatives. Later on we'll see where the continuity of partial derivatives enters into the picture. Well, so what we do is we start changing right, before that actually Rudin points out a simplification which which definitely simplifies the notation. We can assume that m equal to 1. So in other words, the range of the function is to R. Why? So this is part of your homework. So suppose I have a function from u to Rm. F is given in terms of components by f1 up to fm. Then the first thing is, if fi from u to R is differentiable for all I, then so is f. Second thing is, if fi are continuously differentiable for all I, so is f. So for this, so I leave it for you to check these two things. Please keep in mind that for the second one, actually for both of these, one is working with full derivatives as linear transformation, not partial derivatives. So for both of these two statements, you cannot use partial derivatives. You have to work directly with the definition of the derivative. But quite straightforward. So I leave it to you to check these two things. Right.